So in this video, I introduce definite integrals in general. So let's review a little bit. If you have a function f is defined on a closed interval from a to b, with a partition of that interval where the very first x value is a and the very last x value is b, where the x values in that partition are strictly increasing, if you pick c sub I to be any value you want in the ith subinterval from x sub I minus 1 to x sub I, with the change of xi as its length, then the summation as I goes from 1 to n of f evaluated at these choice points times the width of the interval, that's called a Riemann sum of the function for that given partition. Notice there's a lot of variability here. You could have different partitions, and even with one partition you can choose your choice points different ways in every subinterval. With a fixed partition, the sum can still vary greatly due to those choices. Now we have to be careful. Now that the widths of the intervals are not all the same length, taking the limit as just n increases without bound does not mean that the Riemann sums that we form in that sequence of Riemann sums will actually converge to anything. As an example, look at our old friend f of x equals x plus 4 over 4. We have already used a Riemann sum process in a limit using a regular partition where every single subinterval had the same length in order to show that the area was 6. Here though, notice that for this particular Riemann sum, I can change it by just changing the last subinterval. Notice by doing so, I'm getting areas that are increasing. So I'm making a new partition, and yet clearly if I just keep doing this, that since I'm only ever changing the last rectangle and not changing any of the ones before it, that my approximations actually are never getting closer to the area that I'm interested in. So we'll define the norm of a partition to be the length of the longest subinterval. We'll consider the limit process as the norms of these partitions go to 0. So when you say that, if you say the norm is going to 0, that means that eventually I look only at all partitions, no matter how I choose my choice points, where the norm is less than some positive number that's really close to 0, and we can make that norm be as close as we like to 0. So let f of x be a function defined on a closed interval from a to b. If every possible Riemann sum can be forced to be arbitrarily close to one number I by only using partitions whose norms are sufficiently close to 0, so there's a feeling of control, as long as the norms are close enough, all the Riemann sums won't vary very much and they'll all be near the value of I, then we say that the limit of the Riemann sums exists n equals I. In this case, we say f is integrable over the interval from a to b, and the limiting value I is called the definite integral of f from a to b. And it's written as the integral symbol you see here. Notice it's very similar to the antiderivative symbol, but they are not the same thing. This is a number. The antiderivative symbol is a function. Now you have to be careful. Not all functions are integrable. So for example, this one here, if you have a function that is 1 if the input is rational and 0 if x is irrational, please let p stand for just some partition of the interval from 0 to 1. Now given any such partition, you can choose in the k subinterval a irrational value of c sub k. Then the function at that value would be 0, and the Riemann sum, of course, is a sum of 0, so it's 0. But given any such partition again, you could instead choose in the k subinterval a rational number. Then the function at the value is 1, and you wind up adding up the sum of the lengths of all the subintervals, which in this case is just the length of the interval from 0 to 1. That's 1. So in the limit, there's always a Riemann sum that adds the 0, and there is always another Riemann sum that adds the 1. So in the limit, it doesn't matter what the norm does. The limit of these Riemann sums don't always approach one number, as there's always some that add to 0 and there's always some that add to 1. So this function is considered not integrable. So let's look at that limit process again. Consider the case we have a continuous function bounded over some kind of interval from, let's say, something to something, and we're looking at the area between the curve and the x-axis. Consider the cases where the norm of our Riemann sums is fairly large. In that case, you can get a sum of areas that looks like this, or like this, or like that, or like this, and obviously there's a lot of variation in the sum of those areas. But if the norm becomes quite a bit smaller, then all of the rectangles have to become thinner because the norm is the longest such subinterval. So that's the length or the width of all our little rectangles. So we can get this one, or we could get that one. Those are different partitions, but in each case the norm is much smaller. Notice the overall sum of the areas of these rectangles didn't vary that much. But sometimes the limit doesn't exist. Take, for example, this graph. Notice it's defined from 1 to 4. Now, if I make one Riemann sum, that seems like an okay approximation. But notice that one of the subintervals contains where we have a discontinuity. And I can choose the x value to be farther from the discontinuity, making a worse approximation, or much closer to get a much worse, again, approximation. Here, as I choose that choice point, the Riemann sums will vary wildly. They won't approach anything. So in the limit, that limit of Riemann sums wouldn't exist. What we need a condition then is so that the limit of the Riemann sums will exist. And without proof, as long as the function is continuous on a closed interval, the definite integral from a to b of f of x dx will be a number. The limit of the Riemann sums will always exist. In addition, if f is non-negative and integrable over the interval from a to b, then we'll just define the area under the curve y equals f of x over the interval from a to b to equal the definite integral of f from a to b. So this symbol then, in this case, corresponds to area. Suppose instead that f is non-positive. Then the area above that curve over the interval is the integral from a to b f of x dx, but it's opposite of it. Putting these two things together, the integral of f from a to b will equal the net area between the graphs of y equals f of x and the x-axis over the interval from a to b. Any region above or below the axis will count as positive or negative area toward this total. For example, if I wanted to find the area of this one trapezoid, it's the same as the integral from 1 to 4 of x plus 1 dx, because that's the area between the function and the x-axis. Now we know that the area, since it corresponds to a trapezoid, is found by finding the average of the bases. So one of the bases is right here, and that height is found by evaluating the function at 1. So that height is 2. This height is 5. So then the average of the bases, 2 plus 5 divided by 2, times the height between them, and that distance is 3. So this definite integral has got to equal 3 times 2 plus 5 over 2. It is just 21/2. On the other end, though, if I wanted to find this particular integration, this particular net area, it has to equal the definite integral from -2 to 2 of x dx, because this corresponds to the region between the graph and the x-axis, from, in this case, from -2 to 2. But notice that these two regions are congruent to each other. They're the exact same thing. This area, though, will count as positive area. This area will count as negative area. So on the sum, the answer is going to have to be 0, as it's a net sum of those two signed areas. Now we can use the fact that definite integrals sometimes correspond to finding areas of certain regions to find the definite integral. So for example, if I wanted to find this definite integral, I would recognize that if y was equal to the square root of 9 minus x squared, that corresponds to the graph of x squared plus y squared equals 9. It's just a circle, but it's only a portion of it. Now for the circle, I would only be using the top half of it because the y is equal to a positive square root. But in the definite integral, I'm looking only from 0 to 3. So shading the region between the graph and the x-axis for that interval. I only need, therefore, 1/4 the area of the circle. So the answer is 1/4. The radius here is 3, so it would be 3 squared times pi. So this definite integral is therefore equal to 9 pi over 4. Using the same kind of trick here, if I were to draw y equals 2x, that is a straight line going through the origin, but I'm only looking over the interval from 0 to 2. So I shade in between the graph and the x-axis for that interval. I get a triangle. Now the height of the triangle is found by evaluating the function at 2. That would be 4. And the width is 2. So this answer must be 1/2 the base times the height. So that would be 4. And that is how to find that answer. But we can't hope that all our definite integrals are going to correspond to areas of regions that we know how to find. So we need some properties. Here are a bunch of them. Provide the function is integrable over the interval from a to b. Then we have the order of integration property, which says that if you want to take the bounds, the lower and the upper bound on the integration, and swap them, all you do is you put a minus in front. And if you ever integrate from a to a of a particular function, dx, then that would then just be 0. Those two are just by definition. The other one is linearity. It just means that if you find the definite integral of a sum, it's a sum of definite integrals. And if you have a definite integral of a constant multiple, it's a constant multiple of a definite integral. The definite integral symbol then distributes who sums differences in constants. Another property is called the additivity property. A good way to look at it is the sum of the parts is the whole. So in the picture, I've shaded in the area from a to b of f of x dx. I shade in the area from b to c of f of x dx. So then that's the total area. That would then be from a to c of f of x dx. So the picture suggests the truth. Another useful one is the max-min bounds. It says that the minimum value of a function times the width of the interval is always less than the definite integral, which is always less than the maximum value of the function times the width of the interval, which if you look at the picture, it's pretty obvious. Look at the uppermost value, the maximum value. Beneath that makes a rectangle. So the area of the large rectangle contains the area beneath the curve and above the x-axis. So the area of the big rectangle is the maximum y value times the width of the interval, which is in this case b minus a. So this picture then suggests the truth. And if the function is integrable on the interval from a to b, we have the domination property, that if one function's value is always at least as large as another, then the definite integral of the first function is always at least as large as the definite integral of the other. And it's suggested by this picture. You can see the region under the blue graph is clearly larger in area than the region under the orange graph. So the picture once again suggests the truth. All these though I would have to prove. I'm just choosing not to. So without thinking about pictures, let's go and just try to find these answers. I want to know then what's the definite integral from 0 to 6 of f of x dx, using that I know the definite integral from 0 to 2 is -3, and the definite integral from 2 to 6 of this function is 4. So to do so, notice you can write this as from 0 to 2 of f of x dx plus from 2 to 6 of f of x dx, and that's using the additivity property. So this is then -3 plus 4, and that would be 1. This, of course, is 0, as you have a width of only 0. This, by linearity, would be 5 times the definite integral from 2 to 6 of f of x dx, and we know that would be 5 times 4, and that would be 20. And the last one, by swapping the orders, this is the opposite of 0 to 2 of f of x dx, and that's the opposite of -3, which would then be 3. Notice the way I'm writing these. This is what's considered correct work. If you just write down answers, or if you don't use the correct notation, I'd be forced to mark you wrong. This is the kind of work I'm expecting for you to justify your answer in a problem like this. This time, let's assume that f is integrable on the interval from 0 to 6, and this time f will be a function of t. Below is the graph y equals a function of t. Let's just answer the following questions. I want to know what the values of these definite integrals are. To do so, notice that the very first one is from 1 to 2. So that's from 1 to 2. To find that definite integral, I need to know what would then be this area. Well, that area, since the width is 1 and the height is 1, and that's clearly a triangle, that would then be 1/2 base times height, which is 1/2. If I go from 2 to 4, that will then correspond, if you look only in this region from 2 to 4, that also makes a triangle. So to find that definite integral, I find the net area. So the area of this region is, its width is 2, its height is 1. So the area would then be 1/2, 2 times 1, which is 1. But since the region lies below the x-axis, the answer is -1 because it counts as negative area. Now, if I wanted to go and find the definite integral from 1 to 4, you would take these two regions and put them together and find the net area. This counts as +1/2. This counts as -1. Putting those together, that gives you -1/2. If you want to find the definite integral from 4 to 6, here is 4 to 6. I have to find the net area between the curve and the axis. Well, now from 4 to 5, the function's just 0. That would then be just 0 area. From 5 to 6, that would then be a height of 2 and a width of 1. So that area is 1 times 2 times 1/2, which is 1. And that's the answer for those problems. Let's try one more. To show you how you can use some of these properties, I want to find an upper bound on this definite integral. I'm not interested in what it equals. I want to know an upper bound. Well, I know, though, that the cosine to the 4th power, since the cosine is between -1 and 1, the cosine to the 4th power is between 0 and 1. So then, by the domination property, this definite integral must always be less than this one. I'll just replace the cosine with a larger function. But then that is the definite integral from -2 to 4 of 3 dx. And if you think about a graph, here is the function y equals 3. Look at the interval from -2 to 4, shaded in the region between the graph and the interval. The definite integral then must equal the signed area, where anything above the x-axis counts towards positive area, anything below counts negative. Here it's all entirely non-negative, so the answer is just the area of that region. The height is 3 and the width is 6, so that's 18. So whatever that definite integral actually equals, it's less than or equal to 18. Now, just to give you a little taste of how we go about using the definite integral to compute things, remember the process. We often want to take something and to find its value. We think of it as breaking into smaller pieces, finding those values, and then adding them together. So it's a limit of summation. It winds up being that the average value of a function, as long as the function is integrable, is always equal to the value of 1 over b minus a times the definite integral from a to b of f of x dx. That would then give you the average value of the function over that interval. Let's justify that result. Divide the interval from a to b into n equal subintervals. For each subinterval, choose the right endpoint. That will then give me n x values fairly spread out in the interval from a to b. In this case, actually equally spaced out. For each of those x values, evaluate the function. That will then give me n function values. Just average them. That would be the notation you see here on the left. On the right is the exact same thing in summation notation. But then you can bring the constant 1 over n inside the summation, and you can multiply and divide by b minus a and put it inside or outside the summation. But by doing so, rewriting the sum in that way, notice that's the same as this one, because b minus a over n is just the width of the different subintervals. That's a Riemann sum. It's actually a constant times a Riemann sum. We know that the limit of the Riemann sums exists because the function is integrable. That's what it means. But each of these things, each of these Riemann sums multiplied by 1 over b minus a approximates the average value. And all these approximations get closer to one number. So, since in the limit the Riemann sums approach a single value, it must approach the value you have above. It's just 1 over b minus a times the definite integral from a to b of f of x dx. And that gives you a basic introduction to Riemann sums and the limit of them, which is the definite integral. The only thing I have after this video is showing you how to find the value of a definite integral by definition one more time, where we don't have a nice function like x or x squared. We have to somehow be very clever about our choices. You don't need to go further. It's only those who are brave or are curious. Wow, you're still with me. Okay, well, let's go ahead and find the value of the definite integral from 0 to b of the square root of x dx. Now to do that, I can't use a regular partition because the formulas won't work out well. So I'll use a clever one. The partition from 0 to b will be 0, then b times 1 squared over n squared, then b times 2 squared over n squared. The kth such number would be b times k squared over n squared. The very last thing would then be b times n squared over n squared, but that's just b. The width of all these subintervals is the same. It's just the difference in consecutive x values. And I've given you the answer here by subtracting consecutive x values as a function of k and doing the algebra for you. I will also choose the right endpoint in every subinterval. That will then be this value. So let's look at the Riemann sum. To do so, I evaluate the function at the choice point, the square root of b times k squared over n squared. You can now see why I chose the partition the way I did. That way the choice point, when I picked it and I evaluate the function, it's going to be a log cancellation. Then you have the multiplication of the width of the kth subinterval, b over n squared times k, 2k minus 1. Just simplifying that, collecting the b's, taking square root, combining terms, you get that particular sum. Notice that there should be a square root of k squared, but that's k, and I distributed the k into 2k minus 1 to get 2k squared minus k. Then using properties of summation, the constant can come out and the summation will distribute through the function of k, giving you this. But those summations, we know what those are. I gave you formulas for those. So I'll just replace them. And this is the answer so far. So the Riemann sum has to equal this for every choice of n. Whoa, you're still with me. Okay. So then the Riemann sum, being a sum of these areas, is equal to this awful mess. Let's just simplify it. See, the 2 over 6, we'll cancel that. The n cubed, I'll bring it inside the summation, canceling the extra factors of n, giving me this expression. So what I want is the definite integral. It's then equal to the limit of these Riemann sums. Now, if you noticed, in this case, the different subintervals were actually all dependent upon n, and the n was in the denominator. So it didn't matter what k was. If n gets large, all of those get small. So saying the norm of the partition goes to 0 is actually the same in this case as saying just let n become big. So I'll take the limit of the summation you just saw. But if you look at those two different fractions, the first fraction, n plus 1 times 2n plus 1 over 3n squared, in the limit, just use L'Hopital's rule twice, you get 2/3. And the second fraction, n plus 1 over 2n squared, if you use L'Hopital's rule twice or once, you'll see that limit 0. So then in the limit, the answer must be 2/3 times b to the 3/2 power. Now, if you want, you can even go a little further, because the definite integral from a to b of the square root of x is the difference of these two definite integrals by the additivity property. So then you get the definite integral from a to b of the square root of x dx is 2/3 b to the 3/2 minus 2/3 a to the 3/2. That's the answer. Which, I think you agree, that was fairly awful. And it was only for the square root function. Who knows how bad it could be if I made it be just slightly weirder. So don't worry though, there's something better. And that's the next video.